In this lecture, we will look at the derivation of logarithmic mean temperature difference for the counterflow heat exchanger. So now when you look at the counterflow heat exchanger, you will find that your hot fluid enters on the left side with the temperature TH1 and leaves on the right side with temperature TH2. However, your cold fluid enters on the right side from TC1 and it leaves the left side with a temperature TC2. So now in this case, your theta1, normally theta is represented as TH minus TC. So your theta1 is going to be equal to TH1 minus TC2. That is the temperature difference on the left-hand side. So your theta2 is going to be the temperature difference on the right-hand side, which is your TH2 minus TC1. Probably this is the difference that we find in parallel flow and the counterflow heat exchanger. Just like the previous case, here we are going to consider an elemental area over the entire length of the heat exchanger. That elemental area is given by dA. The change in the hot fluid temperature is going to be dTH, and the change in the cold fluid temperature is going to be dTc. Okay. So just like we wrote for the parallel flow heat exchanger, here dQ can be written as U times dA TH minus TC. And it can also be written as minus M dot H CPH TH2 minus TH1, which can be written as minus capital CH times DTH. Or it can also be written as minus M dot C CPC times TC1 minus TC2. Why? Because now the entry is on the right-hand side. We are moving from left to right. So it is going to be TC1 minus TC2. So that makes it negative. So to compensate for the negative sign, we are introducing a negative sign over here. So minus CC times DTC. Okay. So now we can write this as, so your DTH can be written as DQ minus DQ by capital CH. Similarly, DTC can be written as minus DQ divided by capital CC. And now your D of TH minus TC, which is nothing but DTH minus DTC, that is going to be equal to minus DQ by capital CH. Minus of minus is plus, so plus DQ by capital CC. So if you take minus DQ as common, that is going to be 1 by capital CH minus 1 by capital CC. Okay. And this can be written as D of theta equal to minus DQ times 1 by capital CH minus 1 by capital CC. Okay. And we know that this DQ can be replaced with minus UA times TH minus TC multiplied by 1 by capital CH minus 1 by capital CC. That is nothing but minus UA times theta into 1 by capital CH minus 1 by capital CC. So we can say, I'm sorry, this is supposed to be dA. So this is dQ, so we are supposed to call it as the elemental area dA. So d theta by theta is going to be equal to minus U times dA 1 by capital CH minus 1 by capital CC. And now we have the differential form on both sides, meaning it can be integrated on both sides. So this is going to be integrated between the entry and the exit. And this is going to be integrated from minimum to maximum area. So this is ln of theta2 minus ln of theta 1, which can be written as ln of theta 2 by theta 1. And area integrated will give you A. And when the upper and lower limits are applied, it will be A minus 0. So that gives you minus UA times 1 by capital CH minus 1 by capital CC. And just like the previous case, your U can be written as CH times TH2, sorry, TH1 minus TH2. Or it can be written as CC times TC2 minus TC1. So your CH is going to be Q by TH1 minus TH2, and CC is going to be Q by TC2 minus TC1. So 1 by CH is TH1 minus TH2 divided by CC. So Q and 1 by CC is going to be equal to TC2 minus TC1 divided by Q. Now, if that is applied over here, so ln of theta 2 by theta 1 minus UA times TH1 minus TH2 divided by Q minus TC2 minus TC1 divided by Q. We have a common denominator which can be taken outside, UA by Q. And that leaves us with, and this, it is TH1 minus TC2 minus TH2 minus TC1. And if we absorb this minus sign inside, that is going to give you TH2 minus TC1 minus TH1 minus TC2. And so this guy, TH2 minus TC1 is your theta 1, and this is your theta 2. So you have got Q by UA is equal to theta 1 minus theta 2 by ln of, sorry about this, this is theta 2, this is theta 1. You can look at the diagram over here. So TH2 minus TC1 is theta 2, and TH1 minus TC2 is theta 1. So TH2 minus TC1, that is theta 2 minus theta 1. Okay. And so this guy over here is theta 2 minus theta 1 by ln of theta 2 by theta 1, which happens to be TH2 minus TC1, or let me say, okay, minus TH1 minus TC2 whole divided by ln of TH2 minus TC1 divided by TH1 minus TC2. So this expression is your theta m or delta DL. Just like the previous case, your Q can be written as UA times theta m or UA times delta DL. So this is the expression that you have got for the LMTD of counterflow heat exchanger. Thank you.